and welcome to this module on Introduction to Continuum Mechanics. This topic is about the Piola-Kirchhoff stress tensors, and here we discuss the first and the second Piola-Kirchhoff stress tensors. So far, you get to know the Cauchy a stress tensor, or T, where we define a stress tensor in the deform or the current configuration. So here we are in the current or deform. Configuration. So like the previous module, the third chapter of the book, we had like E star, E, B, C, and F, and so many others, uh, tensors to characterize the deformation or the strains in a continuum. Here we also use a different type of stress tensor to characterize the tractions, or the forces and the stress in a continuum. Here so far we use T. We are also going to learn about the second and the first and the second Piola-Kirchhoff stress tensors. So we also have T0, which is the first Piola-Kirchhoff stress tensor, and we also have T tilde, the second Piola-Kirchhoff stress tensor. And here we're going to use these also stress tensors as tools to develop some other some other kind of equations which we may use in different situations. So like the previous module that we used, for example, F in some occasion and E or E star in some other occasions. Here we have a situation where, for example, T is applicable, or for example, T0 suits our our problem, or even T tilde. So it depends on which tool you pick. It is basically a matter of your choice and also the problem that the problem you're dealing with. So if it is uh, easier to use everything in the deform configuration or the current configuration, it's better to use the Cauchy stress tensor. Or in some other situation, which I will mention, it's better to pick, for example, T0, or the first Piola-Kirchhoff stress tensor. So with this in mind, let's get started. So as I already mentioned, we need to actually develop different Piola-Kirchhoff stress tensors, like different deformation tensors, as we would like to, for example, find or calculate the work, or later the power in a system. So basically, from classical mechanics, you know that work is the product of force and the displacement. And basically, the power is the rate of, so if I show D, the rate of work here, so the derivative of work with respect to time. And here, if I replace this work with force and then the product of force and displacement, so maybe it's better to replace this with deformation. So we're required to know which type of force we need to use in here, how to characterize this force. Or here we already mentioned in the third chapter that the deformation here could be D, E star, E, or some other kind of other kind of stress tensors and strain tensors in here, or deformation tensors in here. But we also need to develop their corresponding, basically, stress tensors or force vectors in here. So, for example, you can use you can't use T, for example, the Cauchy stress tensor with, for example, C. It's because C is F transpose F, and this F are 1 plus del U transpose 1 plus del U, and this del U is basically the partial derivative of X, with Xi with respect to capital Xi. So you see here that we are in the reference configuration. So one of the diodes is in reference configuration. So this is not compatible with the Cauchy stress tensor, because the Cauchy stress tensor diodes are both in deform configuration. So they are incompatible. So later we'll learn that, for example, the first Cauchy stress tensor can be used here because one of the diodes of Cauchy stress tensor T0 Ij is, one of them is in the reference configuration and one of them is in the deform configuration. So that's why it is important to pick whatever deformation. So for example, it is important if you pick a deformation which is in reference configuration, I mean, two diodes are in reference configuration, you pick the corresponding tool for the force, or the stress tensor, uh, which both diodes are also in reference configuration. So if you have here one here in ref and the other in ref, both diodes are in ref, then you have to pick the one where this strain tensor here, both diodes should be in reference configuration. So if here you have something which is in reference configuration and the other one is in deform configuration, then you have to pick the corresponding deformation tensor, where the first one is in reference and the other one is in deform configuration. So we also know from the previous modules, I guess, uh, maybe the last parts of the previous chapter 3, that we use this kind of notation like um, E, for example, I, and then we had capital J, or E, small r, capital theta, where we actually said that this is in deform configuration with a small letter, and this is in reference configuration with capital letters. So this is deform, and this is also in deform, and this is in reference configuration. So it matters which tool you pick, and you pick the corresponding stress tensor for your analysis. All right, so get rid of this. Let's get a start by the first Piola-Kirchhoff stress tensor. And the book actually used T0 for this one. So suppose you have a reference configuration like this. Let me just throw it a bit bigger. And this became like this in the deform configuration. So you have the reference configuration, and here you have your deform or your current configuration. So you have an element like dA0 in here. So this is a vector, and this actually deformed like this, and then it became dA, sorry, dA in the current configuration. So you also have a force vector df in here. So let us define df is equal to t. So we already mentioned that this is force per unit area. So we have the force vector, force vector per unit area. So this is the force vector per unit area, so times the magnitude of dA0, and I differentiate between dA0 here. This is like the magnitude, and if I put an arrow, so it indicates this is a vector. So let us define this. And if you notice here, this F here is in deform configuration. And here we define dA0 in reference configuration. So one of the dyads of our stress tensor will be in deform configuration and the other one will be in reference configuration. And I also have to mention that dA is basically the magnitude is equal to dA0 divided by n, or magnitude here. All right. So let us write this 0 in here to differentiate. This is the first Piola-Kirchhoff. So I can define T0 also as T0 and 0. And here I have N0, I know it's known, but I have to find this T capital 0, which I will call the first Piola-Kirchhoff stress tensor. So this is going to be the first Piola-Kirchhoff stress tensor. So far we have df equal to T0 dA0, and then we also have T0 equal to the first Piola-Kirchhoff stress tensor, which we are going to find, and 0. So therefore, I will have df, which I can write as T dA, because this is basically my force in the deform configuration. So I have T dA is equal to T0. So I replace this T0 with T0 and 0. And it might be a good idea to write df as also T dA. So we have T0 and 0. And then we have the rest of the equation, dA0. So here we're going to find TA0. So I move this dA0 to the other side of the equation. This is T dA divided by dA0. And, sorry, this is Tn. So I have, oh, sorry, this dA. And this T in here is T n dA is equal to T0 and 0 dA0. So then I'm going to find T0. So I move this because this is the magnitude. I move it to this side. Then I'm going to have Tn dA dA0 is equal to T0 and 0. And from, I guess, module 2.8. You already know that dA, so here we have the deformed configuration, we have the reference configuration. We can write this as dA equal to dA0, the Jacobian, F inverse transpose, N0, where the Jacobian is basically the determinant of F. So if I substitute this into here, then I get T. So then I have the Jacobian F inverse transpose. And I guess that I missed something in here. This is dAn. So Tj Jacobian F inverse T N0 is equal to T0 N0. So if I take everything to one side, so if I move here, so I'm gonna have T Jacobian F inverse transpose minus T0 N0 is equal to 0. So this is going to be 0. Therefore, T0 is defined as Tj F inverse transpose, or you can simply write this as T Jacobian F transpose inverse. And this is basically the first Piola-Kirchhoff stress tensor. So if I also write this in the initial notation, this is the tensorial notation. So I'm gonna have T0 ij is equal to, so if I write first Jacobian, then I have Tim F transpose inverse Mj, and this is F transpose. So this is going, so I get rid of this transpose and I write Jm in here. So here we found the first Piola-Kirchhoff stress tensor, but we can also write T, the Cauchy stress tensor, in the form of first Piola-Kirchhoff stress tensor. So T is equal to 1 divided by J. So let me write everything in here again, so you can follow what I'm doing. T, so I first write this J because it is scalar, T, F transpose inverse. So first I need to write this as F transpose. Then I also write this as F transpose. So this becomes I, and then 1 divided by J. So I can write T as 1 divided by J T0 F transpose. Or Tij is equal to 1 divided by J T0 I M F transpose Mj, and since this is transpose, I can write this as Jm. And you should also remember that Fmj is basically the partial derivative of x small x m with respect to capital X, partial derivative of capital X m j. And if we just write this as Fjm, so this is the transpose of Fmj, so we are writing capital Xj partial derivative with respect to small x m in here. So here you notice that one of the dyads is in reference configuration and one is in current configuration. So let's see if, so we already know that T is symmetric. But let us see if T0 is symmetric or not. Let's find it out. So if T0 is equal to T0 transpose, then we can call this a symmetric tensor. We already know that Cauchy stress tensor is symmetric, so it means that T is equal to T transpose. So let me write this T0. So TJF transpose. So we know we have TJF transpose inverse. So if I transpose this, and if I shift this right, so what we get is, so this becomes F inverse transpose transpose. So nothing happens to J. Then we have T transpose. So this becomes J. So this becomes F inverse. Then we have T transpose is again T. So you see here that this is this equal to T to J T F inverse transpose? No, they are not equal. Therefore, T0 is not symmetric. So the first Piola-Kirchhoff stress tensor is not symmetric. All right, so let's get to the second Piola-Kirchhoff stress tensor. So second Piola-Kirchhoff stress tensor. But before moving to second Piola-Kirchhoff stress tensor, maybe it's a good idea to mention something, because I wanted to just explain this at the end of the video, but I think it's the right place to mention this. So from your strengths of material course, you remember that we had like true stress, and we had like the engineering stress. So sigma was equal to F divided by A in here. So, and this engineering stress was basically the first area of your component or your part. And the true stress was basically, if I put T in here and if I put E in here. So we had F divided by the area of the component at each load increment. So we also made a connection between these two. But overall, what I'm saying is that this is basically the area in the deform, and also this is the force in the deform. So this is the same as Cauchy stress, and here F was in the deformed state, and here we had A0 in the reference configuration. So basically this was the first Piola-Kirchhoff stress tensor that we used in mechanics of materials to calculate the stress. So I wanted to mention this so you can also get a feeling about what you did during that course. So basically we were calculating the first Piola-Kirchhoff stress tensor. So let's just copy paste this in here. So now let's get to the second Piola-Kirchhoff stress tensor. So imagine a kind of situation where you have your reference configuration like this, and you also have your deform configuration or your current configuration like this, and you of course have a dA0 here, and you have this deformed in dA. So instead of putting F here, like the first Piola-Kirchhoff stress tensor, we're applying a kind of imaginary, or let's say a pseudo or a dummy kind of force in here, df tilde. So this is like an imaginary or pseudo kind of force in here. And now we're going to develop a kind of stress tensor where both its dyads are in reference configuration. So T tilde, the second Piola-Kirchhoff stress tensor, the first dyad is in reference, and also the second dyad is also in reference configuration. So let us define df tilde as T tilde dA0. And here we have T tilde as T capital tilde, which is the second Piola-Kirchhoff stress tensor. And here we have N0 again, because we are in the reference configuration. So we have df tilde is equal to, so instead of T, small t tilde, here we have capital T tilde, N0 dA0. And this is, of course, scalar value, because this is force vector. So this is the stress vector times the magnitude of, this is the force vector per unit volume. So here we have the traction or the stress vector times the area. So we have the force vector in here. And since here we are in the reference configuration, we can use the deformation gradient, like if you remember, we had d small x was equal to f d capital X. So here we are in the deform configuration, and here we are in the reference configuration. So df is equal to fd f tilde. And here, if I want to replace df tilde with df, so I'm gonna just df, so f inverse df is equal to f inverse f df tilde, then this becomes I, so this becomes df tilde. Therefore, df tilde is equal to f inverse df. So from here, we can get f inverse df is equal to T tilde N0 dA0. So we have this df from the first Piola-Kirchhoff from, let me just find it. Here. So this star in here, and then from this square, so from star and square, we can write this as f inverse, and df is T0 dA0 is equal to T tilde N0 dA0. and then I replace this t0 from square. So maybe write this as a square in here. Get rid of this. So I have f inverse, then we have t0 and 0 dA 0 is equal to t tilde and 0 dA0. So these are quantities, so I can get, and not equal to 0, so I can get rid of them. So finally I get f inverse t0 and 0 is equal to t tilde and 0. And I can get everything to one side. I have f inverse t0 minus t tilde and 0 is equal to 0. And finally conclude that t tilde, or the second Piola-Kirchhoff stress tensor, is equal to f inverse, the deformation gradient inverse, t0. This is basically the second Piola-Kirchhoff stress tensor. And you can see, you can write this as, this is the relation basically between the first Piola-Kirchhoff and the second Piola-Kirchhoff stress tensor. So if I write this in tensorial notation, so first and second Piola-Kirchhoff stress tensor is t tilde is equal to f inverse t0, and in initial notation t0 ij is equal to f inverse im t0 mj, and the relation between the second Piola-Kirchhoff and Cauchy stress tensor is basically, so we have t tilde is equal to f inverse t0. So this t0 was equal to, I can find it, so tj f transpose inverse t tj f transpose inverse. So it is equal to this equation here. So t tilde ij is equal to the Jacobian. Then we have f inverse im t mn f inverse. Then we have f inverse transpose nj. And since this is transpose, I can get rid of this t and write this as jn. All right, so now let's see if the second Piola-Kirchhoff stress tensor is symmetric or not. So is t tilde ij symmetric? So if t tilde is equal to t tilde transpose, then we can call this as a symmetric tensor. So t tilde transpose is equal to j f inverse t f inverse transpose. So j is a scalar, I take it out. Then we have f inverse transpose t transpose. Then I have f inverse transpose. So if you have a b c transpose, you know that it becomes c transpose, b transpose, and a transpose. That's what I'm doing here. So this becomes f inverse, then t transpose is t is equal to t, because this is the Cauchy stress tensor. And then we have f inverse transpose. So this is basically the same as t tilde. Therefore, yes, it is symmetric. So T delta is symmetric. So at the end, I guess it might be a good idea to just recap everything into a table. So if I have some rows like this, oops, this one should be a bit longer. So then I write in here the name of the tensor. So we had the Cauchy stress tensor, we had this first Piola-Kirchhoff stress tensor, and then we had the second Piola-Kirchhoff stress tensor here. And we had, our coordinates. So here everything was in deformed configuration. Here, dA was basically the geometry was in the reference configuration. And for the second, this was also in the reference configuration. So about the force, we had this in the deformed configuration. This one was also in deformed configuration, and this was a pseudo kind of force in here. So this was in reference configuration. Deform, or let me write current, maybe. Current. And this is reference. And here we had the area. This was also in, this was in current configuration. This was in reference configuration for the first Piola-Kirchhoff, and for the second Piola-Kirchhoff, everything was in reference configuration. So both diodes here are in current configuration, and here one of the diodes is in current and the other one is in deform. We call them 2-point tensors. One in current and the other in reference. And here everything was in reference, so both diodes are in reference configuration. So here I mean one of the diodes in current configuration and the other in reference configuration. This is also a very nice kind of table that recaps everything about the Cauchy stress tensor, first Piola-Kirchhoff, and the second Piola-Kirchhoff stress tensors. We have an important example in here, which I would like to mention. So this example is the example 4.10.3 in the book. So basically, it says that if A is a tensor of x1, x2, and x3, so this tensor is of these three components, and let's say that we know the partial derivative of the determinant of this tensor with respect to x, capital Xm, is basically equal to the determinant of A times A inverse and J partial derivative of, A Jn with respect to Xm. Then we would like to show that for f, where we know that this f is the deformation gradient tensor, so show that we have this equation in here. So it's the partial derivative of fjm divided by j, and this j is the Jacobian with respect to x, small x. J is equal to 0. So show this ver. So fjm, it's the definition of the deformation gradient. So we have small letter x on the top, and then we have capital letter on the bottom of the fraction, and then we have xj is in the spatial coordinate. It's a function of x2, x3, x1, x2, and x3, and also t, and j is the determinant of f, and it's basically an positive value, so it's not equal to 0. Right, so we're going to start from here in the solution. So let me just change the color of this so you can differentiate between the solution and the problem statement. Right. So if I write this here, so we have the partial derivative of fjm divided by j, partial derivative of xj. So if I take this derivative with respect to small xj, then I have the derivative of the first term in here. So I have partial derivative of fjm with respect to xj times this, so it's 1 divided by j, plus the derivative of the second. So the first term times the derivative of the second. So I have fjm, then I have the partial derivative of j with respect to xj, and since this is in the denominator, then we have minus 1 divided by, sorry, so I may move this a bit to this side. So 1 divided by j squared minus here. And you know that since f is a function of, it, it depends on the material and its spatial coordinates, so j is also dependent. So that's why this term is not equal to 0. The derivative of j is not equal to 0 with respect to small xj. So we have this in here. So we have to use a trick in here, because we're going to basically create this capsule xm in here. So we have to take the derivative with respect to the material coordinate. So to do this, we are allowed to write this, the first term, as partial derivative of jm with respect to capital Xn times capital Xn with respect to xj, plus fjm, so maybe minus fjm divided by Jacobian squared. So this partial derivative of fjm can be written as xn, then the partial derivative of xn with respect to xj. So I'm not putting m in here, because if I put m in here, then we violate the Einstein summation equation. So I just undo these. So then we have xn and xn in here. All right. According to, so I'm just going to maybe copy and paste this faster. So in order to rewrite this equation here, I can basically write this as, since we have fjm, so we can use this in here. So it's the definition. So I substitute fjm with its definition. So it's basically 1 divided by j squared times partial derivative of x. It was jm, so j with respect to x in here. Right. So now if you look at this in here, so we have partial derivative of xj and partial derivative of xj in here. So we can rewrite this term in here as partial derivative of xn with respect to capital Xn. So if I just copy, paste this in here. So then we have the partial derivative of xn with respect to xm, and then we have the partial derivative of j with respect to xn. So here we have the partial derivative of j, which is the determinant of f basically with respect to xn, and this is what we have in here right now. And I can write this as so if I just, so we have the determinant of f, then we have f inverse nj. So yep, so we had the determinant of f with respect to n, and this was m, so this is going to be n, or I can simply write this as if I swap m and n, or you can see from here that this is basically partial derivative of that determinant of f with respect to xm, because now you have partial derivative of xn here and here. So I move this down a bit and write this. This is, sorry, m, and this is f inverse nj times partial derivative of jn with respect to x m. All right. So this determinant is nothing but j, and if I can cancel out this j with this in here, so if I just copy this in here, so then I have minus 1 divided by j, then I have the partial derivative of jn. Here we have xm, so I swap n and m, so it's fjm, partial derivative of xn, and so we swap m and n, so this is going to be f inverse of, let's say, mj. This f inverse is basically capital xm with respect to xj, and I made a mistake here, so it's nj, it's nj. So you can see that these two are equal, therefore this becomes 0. Let's let's write the equation of motion in terms of first Piola-Kirchhoff strain tensor. So far we derived the equation of motion based on let's say the Cauchy strain tensor. Now let's find it in terms of first Piola-Kirchhoff strain tensor, stress tensor, sorry. So equation of motion, so maybe new page. So equation of motion with respect to the second Piola-Kirchhoff stress tensor. So basically, the equation of motion in terms of Cauchy strain tensor was the divergence. So let's write terms of Cauchy strain tensor. It was the divergence of V plus rho B equal to rho A, or in terms of tensorial notation, we had the partial derivative of Tij with respect to xj plus rho bi equal to rho ai. So let's find this equation. Let's write this equation based on the first Piola-Kirchhoff stress tensor. So we have to first find this Tij, the partial derivative of this with respect to xj, and we're going to replace this Tij, the Cauchy string tensor, with its equivalent first Piola-Kirchhoff stress tensor. So we already knew that Tij is equal to 1 divided by j, and here j refers to the Jacobian. T0 I m f m j t, and it's just the the equation that we derived above. So basically I can rewrite this as 1 divided by j t0 I m, and f m j transpose becomes j, it becomes f j m. So I need to derive the equation this based on this equation here. So I simply replace this T0 IMFJM. I just plug it into here, and then I take the derivative. So, sorry, I missed this, just Jacobian here. So I have 1 divided by j in here. Sorry, I have the derivative of the first term, so I'm going to keep j in here. So it's better to write it like this. So we have T0 I m, then we have f j m, then we have Jacobian here. So this is one term, this is another term. So we have the derivative of T0 I m with respect to xj, fjm divided by the Jacobian, plus T0 I am partial derivative of partial derivative of the whole jm divided by the Jacobian with respect to xj. And from the example we already solved in here, we showed that the partial derivative of fjm divided by the Jacobian, this partial derivative with respect to xj, from this example, 4, 10, 3 is equal to 0. So this is 0 from example 4, 10, 3, 4, 10, 3. So we only are left with this equation here. So I can also write this as the partial derivative of t I m with respect to x 0, because I'm going to create this condition that t0, if you remember, one of the dyads of the area, the dyad related to area, it was in the one of the dyads, sorry, this one, the area, was in the reference configuration. So based on this, I'm going to just rewrite this expression here as partial derivative of x n. So the same strategy I used in example 4.10.3, xj, and fjm is basically the partial derivative of xj with respect to capital Xm, and then I have 1 over j in here. So this in here can be written as partial derivative of xn with respect to xm, which is simply delta nm. So this is equal to the partial derivative of t0 im with respect to capital Xn. Then we have delta nm, 1 divided by j. Or maybe it's a good idea just to shift everything. Sorry. So if I shift just a bit, 1 divided by j in here. So for this to be not equal to 0, so n should be equal to m, 1 divided by j, partial derivative of t0 im with respect to xm. Or I can just replace this m with j. So 1 divided by j, partial derivative of t0 ij with respect to capital X j. So basically, you see that this term in the Cauchy strain tensor became this term. So 1 divided by, so in terms of first, so um, let's say the equation of motion with respect to, or in terms of second Piola-Kirchhoff stress tensor is basically 1 divided by j, partial derivative of t0 ij with respect to capital Xj plus, so these two terms, they remain the same. Rho bi is equal to rho ai. So if I just get rid of this j in this term and just multiply these terms by j, so I get t0 ij, and this j value is also positive, so this remains positive. This doesn't change signs. So here, sorry, this is rho j ai. So from previous module, I mean the module 2 or chapter 3 of the book, we already showed that rho j is equal to rho 0. So I can replace this with rho 0. So then everything will be in the reference configuration. Plus rho 0 bi is equal to rho 0 j, sorry, rho 0 ai. And this is the equation of motion in terms of second Piola-Kirchhoff strain tensor. So know that these AI here and this BI in here are with respect to the material coordinate, not the spatial coordinate. So basically, these are functions of, let's say, so AI is a function of capital Xi in here, and BI, of course, is a function of capital Xi. However, for the Cauchy strain tensor, so if I can if I bring the equation, let me just write it down in here. So for the Cauchy strain, it was the partial derivative of t ij with respect to xj small x plus rho bi is equal to rho ai in here, and this ai is basically a function of small xi, and this bi was a function of a small xi. So be careful about this.